Now, based on the lectures related to stress transformation and strain transformation, let's solve some example problem. So the first problem is related to Mohr circle strain analysis for a plane stress problem. Okay, so so this problem, the details are as follows. So for a plane stress problem, suppose that principal stress are given as sigma A, sigma B, and sigma z equals to be 0. Okay, and here note that sigma a is larger than 0 and sigma b is smaller than 0, which is negative number or compressive stress. And because this is principal stress, or strain stress component are 0, and the absolute value of sigma a and is larger than absolute value of sigma b. Given these stress state, and the problem also gives you the material property, Young's modulus E, and Poisson ratio nu, and this problem asks you draw Mohr circle using strain. Okay, what will be the Mohr circle strain analysis with this kind of stress state? Okay, here you have to make assumption that nu is larger than 0. Because I told you that nu can be -1 and positive 0.5. Okay, so that's the range of the nu, and if nu, even though nu can be a negative number, if nu become negative, the answer can be different. We'll just assume nu is larger than 0, for typical most materials. So let's draw the Mohr circle for stress analysis, sigma and tau as horizontal and vertical axis. Here we have sigma A positive, sigma B negative, and sigma Z, which is 0, 3, our principal stress, and the absolute value of sigma A is larger than absolute value of sigma B, so that you have sigma B, sigma 0, sigma Z, and sigma A. And after pointing out 3 principal stress, you can draw 3 circles. Then you can complete Mohr circle for stress. Okay, so here this is typical Mohr circle for stress, where you have one stress component which is 0, and the other stress component is non-zero. Okay, so having obtained this Mohr circle for stress, the problem asks us try to draw Mohr circle for strain. And to draw Mohr circle for strain, we have to find principal axis and principal strain for strain. However, in previous lecture, we learned that principal axes are identical between stress analysis and strain analysis. Okay, so we can recognize that x prime, y prime, g prime axis, which is given in the original problem, should be principal axis, and we can simply utilize the generalized Hooke's law. Okay, so out of the generalized Hooke's law, which we obtained in we wrote in previous page, we have this relationship. The strain component and normal stress component, they are related like this. So if you plug in sigma x prime is sigma a, sigma y prime is sigma b, and sigma g prime is 0, and if you plug in sigma a and sigma b, you have the first strain component epsilon a written in this way, second strain component epsilon b written in this way, and you have third strain component which is epsilon z prime written as this. Okay, so here, even though you have sigma z equals to be 0, you have a sigma a and sigma b for sigma x prime and sigma y prime. After plugging in sigma a and sigma b in these two positions, you have minus nu over e sigma a plus sigma b. And because the absolute value of sigma a is larger than absolute value of sigma b, and this is negative number, and after summing up these, you have still positive number. You have a negative sign here, and I told you that nu is smaller than 0, so you have a negative number. No, it's larger than 0. You have positive number and positive number. Epsilon g prime, which is epsilon c, is smaller than 0 due to this negative sign. Okay, and the sign of this guy and sign of this guy is not has not changed. Okay, so after identifying epsilon a and epsilon b and epsilon c, we found that for plane stress problem, if you draw Mohr circle for stress, one principal stress is located at origin. However, if you convert that to Mohr circle for strain because of the Poisson ratio effect, and if this is non-zero, you have third principal strain is out of the origin. Okay, so that will be the difference between Mohr circle for stress and Mohr circle for strain when you consider plane stress problem. Okay, so this is our first problem. Now let's solve the second problem. Second problem considers real numbers. We only considered some alphabets in previous problem. Second problem, we're gonna solve a problem with real numbers, measured numbers. So the second problem asks us this question. At the surface of a machine component, it should be free surface. When you have this machine component where we don't have any surface shear stress and surface normal stress, you measure principal stress at some point by using strain rosette measuring three strain component. You can identify epsilon x and epsilon y and epsilon gamma xy. After three component of strain, you can obtain principal strain, in-plane principal strain out of the Mohr circle for strain analysis, and the result turns out to be this: epsilon a along one direction, along one principal axis is 410 to the negative 6, and along the other principal axis, you have negative 50 10 to the negative 6 strain. There is no dimension for strain, and the Poisson ratio turns out to be 0.3. So the problem asks two questions: what is the maximum in-plane shear strain, and what is the true value of maximum shear strain? Because the first question asks Mohr circle for strain in 2D, and second question asks Mohr circle for strain in 3D. So for the first problem, from Mohr circle strain in 2D problem, what you do is, it's very simple. We already know two principal strain, epsilon A and epsilon B, and epsilon A and epsilon B has value of negative something and positive something, and you identify that the top point corresponds to maximum in-plane shearing stress divided by 2, because the vertical axis is gamma over 2. So out of this equation, and the radius is given as epsilon A minus epsilon B divided by 2, you can recognize that maximum in-plane shearing stress is same as epsilon A minus epsilon B, which is 400 plus 50. So that 450 10 to the negative 6 as the maximum shearing stress value. Now let's solve the second problem. What is the true maximum shear strain when considering full 3D? Okay, so here you may wonder, we may miss one information. However, I told you that we are considering the surface of the machine component, so that there is no normal traction or shear traction. In that case, you can consider this as a free surface, and for the free surface, you can see that the stress along the out of plane direction is 0. So for plane, for this problem, you can consider that as a plane stress problem. Okay, so for plane stress problem, you can identify that this problem is quite similar to previous page, where we consider Mohr circle for strain analysis for plane stress problem. Okay, so from previous page, we can immediately notice that epsilon c can be written as minus nu over e multiplied by sigma a plus sigma b. Okay, so this expression, you can identify epsilon c, the third principal strain, out of Poisson ratio and Young's modulus, and two normal strain, in-plane normal strain, epsilon sigma a and sigma b. However, the problem only gives us normal strain and Poisson ratio, and there is no information about Young's modulus. In the absence of Young's modulus, which would give us the principal stress out of the principal strain. Of course, there is more terms here. In the absence of Young's modulus, you cannot obtain sigma a and sigma b. However, even though we don't have sigma a, sigma b, and e, we can still obtain epsilon c out of the epsilon a and epsilon b, and let's see how to do that. So what you can realize from previous page, page 6, is that if you add first equation and second equation, the left hand side becomes epsilon A plus epsilon B. Right hand side becomes some equation including sigma A and sigma B and nu and E. But what you can realize is that if you sum up the right hand side minus nu over E sigma A plus sigma B. So you can somehow massage the right hand side and take out sigma A plus sigma B, and you do e to the 1 minus nu. Okay, so that will be the right hand side of the equation 1 plus equation 2. Okay, so after recognizing that, you can realize that 1 minus nu over E multiplied by sigma A plus sigma B is same as epsilon A plus epsilon B. Or in other words, if you rewrite in terms of sigma A plus sigma B, it's same as E over 1 over nu multiplied by epsilon A plus epsilon B. So if you plug in this expression to here, you can get rid of Young's modulus, and you can find that epsilon C can be written as a function of Poisson ratio nu and epsilon A and epsilon B. So if you plug in 0.3 for nu, and if you plug in 400, if you plug in negative 50 and multiply 10 to the negative 6, what you're going to realize is that epsilon C is minus 150 multiplied by 10 to the negative 6. Okay, so with this, you can identify epsilon A, epsilon B, and epsilon C. And this guy is 400, this guy is negative 50, this guy is negative 150, and you have this unit. Okay, so if you identify epsilon A, epsilon B, and epsilon C and complete the Mohr circle, you find that the Mohr circle for 3D would have larger radius than in-plane Mohr circle, and the true maximum shearing strain for 3D analysis is same as epsilon A minus epsilon C. Okay, the equation is same as previous page, but instead of epsilon B, you have to use epsilon C to obtain the radius for largest circle out of 3D analysis, and it turns out to be 550 10 to the negative 6 as the maximum shearing stress value for full 3D analysis. And if you have the failure strain of the material, you have to compare this maximum shearing strain with the material property. Okay, so here we had some interesting analysis including the strain. So today we learn how to measure the strain and what is the relationship between Mohr circle strain and Mohr circle for stress, and based on that discussion, we solved some problems including plane stress state, but utilizing the strain Mohr circle. Okay, so with this, let me finish my lecture on stress and strain transformation. And based on all of this discussion, we'll discuss about the design of reliable structure, considering combination of complex like normal and shear stress state. Okay, including 4 reactions: N, V, T, and what is the other? N, V, T, and M. Okay, so including 4 reactions. We'll try to consider a reliable design analysis for realistic structure in next chapter. Okay.